Okay, so I'm Mamadou Sek from Old Dominion University, the Engineering Management and Systems Engineering Department. And in this presentation, basically, I want to present a conceptual model for modeling and simulating infrastructure systems. And basically, in this presentation, I will focus on basically the paradigm of modeling, what are the underlying assumptions, and so on. So I'll not be talking very technically about modeling and simulation, no equations, and so on and so forth. I'll mostly focus on the underlying conceptual model. So basically, I will talk about the... Okay, so the slides are a little bit moved around. Probably we used a different version of Microsoft PowerPoint, but essentially most things will be there. So I'll talk generally about what is the objective of this modeling exercise, what is the underlying paradigm that we adopt, give a set of definitions that underlie the conceptual model, and then eventually show that conceptual model and its different components. So what is my objective with this research? Basically, the goal is to understand how infrastructure systems co-evolve with, on the one hand, society and nature. Okay? So as we've heard in different presentations, we cannot really understand infrastructure strictly from a technical perspective. Infrastructures exist and interact with society on the one hand, so demographics, policies, institutions, the economy, and also on the other hand, nature, that is, what are the resources that are available and how does infrastructure interact with existing ecosystems. And furthermore, beyond this curiosity of trying to understand how this co-evolution occurs, as an engineer, we want to enact some change to make things better. So the second objective is how we can use modeling to understand how to best influence this co-evolution. So if we want to, for example, participate in a green transition through infrastructure, how can we do that? Okay. So now about the paradigm. How do we look at infrastructure systems? And to explain that, I will use this picture by Dursa and al. From 2013. And basically, this gives us an intuition that when we look at systems in general, when we look at natural systems, going from the least complex to the most complex natural systems, we go from least architected to more architected. So when you look at for example, tissues in an organ, you have less and less organization versus when you look at whole organisms or very complex organs, such as the brain. So when you go in natural systems towards more complexity, you go from least architected to more architected. Conversely, when you look at artificial systems, the simpler artificial systems are highly architected, and we talk generally about complicated systems and not complex systems. For example, a computer, hierarchically organized with well-known components that are modularly or defined with very good interconnections and interoperability. When we go further in complexity into artificial systems, let's say cities, for example, or what emerges from social networks and infrastructure, we get into less and less architecture because these systems have evolved historically with many local changes that lead to a structure that is not as neat as the complicated architected systems. And basically, so infrastructure is in this place here where natural systems and artificial systems meet in terms of complexity. So these are systems that are presumably designed by societies, but they display some properties of complexity and self-organization and so on. For that reason, we regard infrastructure change as pseudo-autonomous. We almost adopt a naturalistic perspective, looking at infrastructures as if they were natural systems that evolve according to their own dynamics. So there is a long-term evolutionary and developmental process that has its own rules and mechanisms. And basically nature and society work as an ecosystem for that infrastructure to develop and emerge. Okay? And coming from a systems engineering department, this is a very interesting feature for me, because generally when we teach systems engineering, we tell students about the importance of having well-defined, stable requirements, identifying all constraints in the first place, and then going through the traditional waterfall process to design the system. And of course, this works well when you design a piece of software. But this doesn't work on infrastructures, because these are really complicated systems, very complex systems, and to some extent beyond our cognitive capacity to fully grasp at any point in time. And basically, as engineers, we are reduced to triggering local adaptations on the system. And by local, I mean both local in space and in time. Okay? So we have to shift the paradigm in systems engineering when we engineer these complex systems of systems from someone who looks at the system at the micro scale with a large amount of control over the system's state space to basically someone who tinkers locally with the system and basically having this multi-scalar approach, trying to link the micro, the meso, and the macro scale of the system's evolution. So basically, from that perspective, what then are infrastructures? The main role of infrastructures is to mediate the relation between society and nature, to minimize mismatches between needs and resources. So society has needs for energy, water, goods, and it has institutions, it has centers of knowledge, it has businesses, different actors with different interests and perspectives. And we have nature that provides some substances and has some ecosystems that can be influenced by infrastructure. And basically, infrastructure is a sort of supply chain, a network that goes from some resources to some needs, basically transforming it stepwise until it can benefit society. So basically, infrastructure is just that network. And also to underline that complexity, infrastructure is really fundamental to modernity. Our mode of life cannot be understood without infrastructure. And one could say that it is as fundamental to our way of life as mobility would be to a nomad. So nomads move around to alleviate those differences between needs and resources from season to season. Infrastructure basically is an artificial system that we build to bring nature towards us. Okay, so it's a different way of seeing things. And I talked about needs and resources. Basically, those are just substances of different natures. So energy, for example, electric power, heat, information, image, voice, control, data, or matter. Could be water, goods, food supplies, and even people in their physical nature trying to move from one place to another. And both needs and resources are just that, and they are characterized by a number of properties which make infrastructure necessary. So these substances are characterized first by the actual nature of the need. So it could be electricity with a set of parameters, for example, a certain voltage and amplitude, the quantity that is needed and at what time it's needed, and the physical location. So you see that there are some patterns of these things. For example, the availability of solar power in some places is different than it's available at other places. And the needs also are distributed geographically. So you'll see that these are the places in the US where the intensity of light used is much higher than other places. So we have these different features, and basically the differences between these features creates mismatches. So three categories of mismatches in the model. You have what we call substantial mismatches, is I need a certain resource at a certain place, but I only have other resources available there, and those other resources could be a precursor for the resource that I need. Locational mismatch, which is that I need a substance at some location, but it's only available at some other location. And temporal mismatch, which is that I need a substance at some point in time in some quantity, but it was only available at a surplus at a certain point of time before. And basically, technologies are designed to deal with these mismatches. So we build networks with technologies, for example, a mine, coal mine, and then a power plant, and then we have a road network to transport the coal between the places, and we have this power plant that transforms the coal into energy, and so on and so forth. And because these mismatches are not stable in time, when we think about it at the macro scale, cities get more populated or less populated, so we need more of the resource, and so on and so forth. The network becomes complex and adaptive. So it means that we need to create new nodes, delete some nodes. We have alternatives between transporting first and transforming, or transforming and then transforming. So basically, this network is a complex adaptive network. So the technologies that we're talking about, basically, they are a transformation function. And this transformation function has three parts. We have operands, which define the input. So a gas power plant will be basically a function that has as operands natural gas, air, and water. Through this transformation process, produces high voltage power, nitrogen, CO2, water, and other things. So basically, every technology will be this cybernetic transformation function that takes some operands, puts them through an operation, and generates some transforms. So in management of technology, we know that these technologies have distinct functionalities. So processing is what alters the nature of a substance, whether that is a matter, energy, or information. Transporting, which alters the geographical location of the substance. And storing, which prevents or delays the natural dissipation of the substance. So these are the three classes of technologies that exist. And basically, these technologies alleviate the same mismatches that we talked about. So substantial mismatches will need processing, locational will need transporting, and storing will deal with temporal mismatches. Technologies also have some non-technical lifecycle attributes that affect how infrastructures change in the historical scale. So how cost is distributed, whether the initial cost and the operational cost. Where is the technology in its life cycle? Are we in the innovation phase, the growth or the maturity phase? And how is the efficiency boundary of that technology shifting? Okay. So, for example, the amount of energy that you can generate by a solar module has been increasing in the past 50 years, if we compute that. So basically, this leads us to the high-level view of the computational model that we have built. So we have society on the one hand, made of population agents and polity agents. And polity agents are basically the governance agents who manage and control these population agents. These population agents have a set of needs. These needs are substances as we defined, being energy, information, or material. In the same way, nature can be subdivided into zones which have resources available, these resources being as well substances. Okay? And then infrastructure, as we said, is something in between that manages the mismatches between these two subsystems. And the operands and transforms of technologies are substances, and the operation can be processing, transporting, and storing, which basically will alleviate the mismatches that we've defined before. So this is the core conceptual model underlying the simulation. So that's the static part. If you think about the dynamic part, what will generate change in the system, basically we go back to the same point that our instantaneous capacity to operate transitions is limited in different ways. Both first bounded rationality, I spoke of our cognitive limitations of understanding the whole system. Capacity limitations could be money, for example. We may have the best ideas today about how to make the world better, but we don't have the budget to make those radical changes immediately. So sunk costs and so on. And also very important is bounded authority. So generally, we only have local control over the transformations that we can operate. And for that reason, the changes are at best locally optimal in time and space. And this creates the importance of contingency. So a few years ago, when we were working on a project with the Port of Rotterdam, just after the 2008 crisis, there were large plans that were figured out for the Maasvlakte 2 port. But then the crisis hit, and the number of containers being transported was reduced by a large percentage. Basically, contingency is just that. So when you look at these systems in the historical scale, local changes have a large impact on how things will look like in the future. And basically, that leads us to the idea of generative entrenchment. So the early decisions that you make in a long-term trajectory in the developmental time of a system have a lot of causal links associated with the ultimate changes that you will make. And this is what locks us into systems. So when you make a decision here that looks like a great decision, and you make investments into it, you have compatibility and sunk costs that will constrain the later decisions that you can make. And sometimes that comes only from contingency. So what locally is this state of affairs? So when we think about the macro scale, we have things such as how recessions occur, how population ages, migration dynamics, how environmental awareness changes. So these are things that you can consider with a macro model with a time scale going from 30 to 100 years, how these dynamics are affected. However, in a 1 to 5 year time scale, you perceive some service deficits, or you anticipate some service deficits, you generate alternatives, you make decisions about those alternatives, and you implement them. But that is really something that occurs in a very tiny subset of the total space in which these infrastructural dynamics occur. And this is basically the waterfall thing that we teach to every engineering student. So basically, the engine of change is that perceived or anticipated service deficit. For example, changes in demographics, changes in standards of living, technological opportunities, technological obsolescence, policy and regulation changes. And basically, you need this upward and downward causation that links the microscopic timescale and the macroscopic timescale to have an adequate simulation over the long timescale. So once a service deficit is perceived, there are multiple options based on the technological landscape that we have at that point. And I talked about mismatches, temporal, substantial, and locational. Basically, the same situation can be interpreted by an agent given the technologies available by either of these. And basically, this leads to what technological choices you will make. Either implementing storage technologies or transformation technologies or transport technologies, or a combination thereof. So for every perceived service mismatch, given a set of technologies available, you have a large set of basically design choices that are available at the local time scale. And basically, as a decision maker, you are a discrete choice, utility maximizing agent. So you're trying to make a rational decision in the local time scale, considering costs, quality of service, risk, population acceptance, economic impact, and basically operating according to that bounded rationality situation. And we can also say that we will have functional equivalence over all these choices. So I can decide to implement, let's say, a solar farm with some storage batteries, or I could create a electricity transmission line from an existing substation to the location that I'm trying to serve. So from a functional perspective, electricity will be available. The main divergence is non-functional, so the quality attributes of the system: sustainability, cost, reliability, evolvability, and so on. Basically, this brings us to the computational framework that we are currently developing. At the top level, we have a systems dynamic model that has a population dynamics module, an economics module, and an opinion diffusion module. So this is really operating at the macro scale. At the bottom here, we have a GIS implementation where we can map the resources, the installed technology, and track things like carbon emissions and things like that. We have a module that uses logistic regression to simulate technology dynamics. Basically, each technology will be put in the S-curve, and depending on how much of it is implemented, we will shift the efficiency boundary for that technology. And then the thing that really affects the change is the quality agents that are implemented as utility-based decision-making agents that basically at every local time step will need to identify those deficits and maximize their local utility function to maximize criteria that are specific to each of the agents. And basically, we have these loops, these feedback loops that go from the micro to the macro. So technology dynamics is a macro feature, and basically population dynamics, the social system is also a macro system, and basically this implements the micro component. So therefore, we will have a upward and downward causation in this direction and in this direction. In summary, so we've explained how infrastructure systems co-evolve with society and nature, and that any model that would try to understand how infrastructure evolves over long time periods would need a module about society and nature. That we need, therefore, a multi-scalar view that links the local tinkering and the long-term change patterns. This leads to a complex adaptive network that emerges as local decisions are made. So we need systems, dynamics, agents, geographical information systems, and logistic regression. And the framework is currently being developed by myself and our PhD students at Old Dominion. And our first case study concerns rural electrification in West Africa. So what technology should we implement? Should we implement solar or diesel or other technologies? at the local stage, and how does that affect the ecosystem? How does that affect economic opportunities that will emerge in that region? So, in short, that's what I had on the conceptual model for a framework on infrastructure evolution. Thank you.
So I decided to go a little bit of a different direction with my presentation, somewhat last minute. Tell you a little bit more of a story, maybe a narrative, but I think it builds really well on your presentation. A lot of the same elements. Let me see if I can get this to work. This is Antarctica. It's the closest one can get to being on another planet while you're still on planet Earth. That right there is Bird Surface Camp, and it's sitting on top of 7,000 feet of ice in the middle of the Western Antarctic. It is the driest, coldest, and most inhospitable environment on the planet, yet we still manage to exist there. The only way to survive in such an environment, and more so function and be productive, is to set up an interface. That interface is a system of infrastructures that allow us to access and provide ourselves with critical resources in an out-of-context context. Simple infrastructures often need to be simplified further because aspects we take for granted don't function in Antarctic conditions. You know how duct tape supposedly fixes everything? Well, down there, if you don't perfect the speed necessary to stick it to itself, it dries up and freezes before you can apply it to any surface. When we get there, we basically placed the infrastructure from the previous year, the previous austral summer season, on pallets, and we get there, we have to dig it out from the winter and then rebuild it. And this is all for science support. And the mission takes about 4 to 5 months being out on the ice. It's basically infrastructure down to the bare minimum. It's the raw elements and really gives you perspective of what it takes to sustain humans and to sustain a society of sorts. Once we establish an oasis in the desert, we can then use it as a staging point to venture further. Those 3 small lines right there is a traverse, the pig traverse, that's heading out a few hundred miles towards the coast where they're going to establish a new camp. Teleport across the world to another harsh landscape. This is a Black Rock Desert. It's beautifully desolate until late summer when the 3rd largest city in Nevada rises out of the dust for a single week. And forgive, I had some technical difficulties. Play the video in a second. Some of you have heard of Burning Man. One of my roles is a logistics manager for one of the volunteer departments for the Black Rock Rangers, which is a sub-department within the Burning Man organization. It's an arts festival that brings together an upwards of 70,000 people in yet another fairly inhospitable environment. I just got back actually 3 days ago from 3 weeks in the desert. You may have heard of it described as a massive rave, a hippie party, or possibly even a haven for heathens. And while these elements do exist, as they do in every city, by the way, really just on a smaller scale, it can also be less sensationally described as a social experiment, an evolving attempt at utopia, and even as a hub for entrepreneurial networking. It is all of these things, and again, it would not be possible without infrastructure. The infrastructure here is brought, well, there's the event infrastructure, which is bought by the org itself, and there are many volunteers and staff that come out and build it over the period of a couple of months. And then the main body comes, which is the participants, and they all bring their own infrastructure. A lot of people who've never been there before and don't actually know what it takes to survive in this kind of environment. You get crazy winds, dust storms. The temperatures can vary. This year there were close to 100 and down to 32. Government and military types like to joke that it looks a lot like a refugee camp, in this case for hippies, and as such they too come to the event and test out new infrastructural technologies in harsh arid winds, corrosive alkaline dust storms, and no access to critical services outside of what they must bring themselves, systems which in themselves don't always function, normally anyway. What they do forget, however, is once they join the event, they too are considered hippies. An example of such experimentation at Burning Man was done by the DARPA-funded Strong Angel project, which initiated a series of exercises intended to improve coordination between military operations and civilian-led relief efforts. The team practiced setting up shelter frame kits, deploying communication infrastructures, and even turned Pringles cans into Wi-Fi antennas. Range Networks, another group, tested out a BYOD, bring your own device, SMS communication network using an antenna built up from scratch. As far as participants go, a lot of people work year-round on art installations or performance installations and then attempt to erect them in this environment, and they don't always last. I've seen big installations break during the first storm, and then for the rest of the event, they become evidence of how things can fail. The playa environment, we call this the playa, the dried lake bed. It's not unlike post-disaster environments, conflict zones, and the impoverished developing world in that it provides minimal or broken infrastructural systems, extremely limited resources, and rapidly changing conditions. Mind you, that is also where the comparison ends. These infrastructures, tested out in a social environment that not only fosters but encourages experimentation, can then be refined accordingly and be perfected to be more resilient with better default world applications. Resilience, we've probably heard over the past couple of days, there's all sorts of definitions of resilience, depending on background or context in the world or situation in the world or what you work on. But the common theme that is being able to adapt to change and to go with it. It being nature, conditions, societal advancements, technology, climate. But the problem is that we're not really doing that. We're not really going with it, right? Infrastructurally speaking, we're kind of terrible at going with it, and we tend to resist change. We seek stability. The catch-22 here is that the way to secure stability is to be able to go with the flow, and that thing that we resist. How do I get back to the... Can I get back to the screen, to the slideshow? Thank you. In Antarctica, resilience is this guy. He was our mechanic. And without him, our mission would likely have failed the first day that we got there. He's the one who immediately set to getting the bulldozer to function once we dug it out from its frozen winter grave, so that we could then uncover the rest of the infrastructure pallets below multiple feet of drifting snow and ice. And then if you see that line way in the back, that is the electrical posts that were set up of where we're going to set up the infrastructure, like the commissary tent and the mechanics tent and the operations tent, the scientists tent, etc. He has the ability to understand the underlying principles of how machines and engines work and apply these principles across the board. If our heavy equipment seized up, or the fuel pumps froze, or the ice melting machine, our only source of water, broke down, he was who we relied on. And if he wasn't there, we probably would have had to abort or, find somebody else, but that can be hard. Back on planet Earth, we tend to institutionalize these roles. We hire for specialization. We compartmentalize knowledge, form more and more subcategories of research and development, and practically segregate disciplines. But don't get me wrong, these specializations are important. But what we lack are the cross channels to bring them, the means to form interconnected open systems across these closed systems, bring them together. This would increase our resilience. I was really happy here to speak, especially last night when the posters were being presented. I was speaking to students from various backgrounds. One of the students was a physicist, and I don't know if you spoke to him or saw his poster. I think he's maybe here, not sure. And they were mapping transportation flows using different methodologies. But anyway, it was interesting to see a physicist applying their methods to infrastructure. I don't usually come across my background's in architecture, and I've done a lot of different humanitarian aid and disaster response and worked in Antarctica and Afghanistan and post Sandy. But usually it's people who are pretty specialized in these response or very specifically engineering and technological areas. But it's not often that you get people from another discipline who's working on that problem with you. But when it does happen, it's kind of amazing, and you can make some huge leaps. I have another video. If infrastructure is our interface with the environment, the way that we access resources, the foundation atop which we build society, then shouldn't infrastructure be called back into focus? In the developed world, we take infrastructure for granted. We in the developed world are so accustomed to having critical resources readily accessible that the systems that make that possible have been rendered practically invisible in the day-to-day. Imagine if we brought infrastructure, its purpose, why we have it, why we need it, why the way we design it matters, back into focus. What if it were made visible again, mostly figuratively, but sometimes literally? Imagine if more disciplines had an infrastructural lens that they peered through, or an infrastructurally minded sub-department, the Ecological Infrastructure Lab, or the Climate Design Infrastructure Relationships Department. We need mediators, translators, and communicators to bridge these gaps. If we're to increase resilience and sustainable practices, if we're to catalyze the sort of paradigm shift that's needed to change the way we think about and create infrastructure, we must increase multidisciplinary discourse around these topics. And this is where I would like to invite all of you. I don't know all of your backgrounds or where you work, but we have a shared interest here in infrastructure. And I don't know even what the solution is yet, but I would like to find a way to create these bridges. So I'm happy to get emails and suggestions. There's an importance of relationships. We got to pull the right people, the specialists, towards a common challenge to work together. Otherwise, people die. The importance of relationships is the need for multidisciplinary cooperation and communication. We can't continue to think and plan infrastructure in silos and only specialize. Society is increasingly connected. It is time we increase our connectivity in the physical world as well. Those physical and temporal systems that you were talking about, it is complex, and it's getting more complex, what with climate change. And nothing in austere environments exists in social isolation. Critical infrastructure and services are fairly, critical. So the social infrastructure, the ability to pick up the radio and call in the resources, or to be able to, post-disaster, find the other people working at the other end of what you need and be able to connect those dots. And use the community who are also hopefully aware of those infrastructures that are needed. That is how we can become more sustainable and resilient. Without designing, planning, and building infrastructures based on relationships between humans and environment, and including the overlapping relationships between ecological elements, we will continue to be wasteful, inefficient with our use of resources, and failing the entire ecosystem of which we are a part. So resilience, there's too many definitions, but I think the more we work together, the closer we can bring that definition to a common goal. Thank you.
Thank you both. I'll now open it up for questions. There's a microphone in the middle of the room if you have a question for our speakers. Anyone?
Seeing as no one else is asking any, I'll ask a question which maybe is not the right one, but I was thinking of this in one of the earlier presentations. I forget now which, but it's really, I think, a question for our first speaker about your framework. You were talking about how you would have your first initial application to the evaluation of some infrastructure investment choices in Africa. I forget now, what was that? Electricity? Power?
Yeah, rural electric power.
Yeah, so you were going to look at the, you said ecological impacts, economic impacts. Now, you know, I'm an economist. I've specialized in transportation for quite a few years. And as an economist, we're often looking for some application of benefit cost analysis to produce some summary measure in dollar terms of the overall benefit and cost to society. So, you know, to the extent possible, it would combine and monetize these various impacts you're talking about: ecological, economic, social. Put as much as you can, a price tag on everything. So I was wondering, in your thinking about infrastructure modeling, to what extent you would endorse that sort of approach, see it as feasible, or so it's really a two-part question. That's part of it. I mean, or is really all you can do just produce these various measures of impact and leave it to the decision makers to sort it out and decide, is overall this option better than that option? The reason I'm thinking of this question really is partly, you know, you were talking about how your modeling framework includes utility maximizing agents. Something that I've often said in my own field, transportation and benefit cost analysis. When you do that type of modeling, basically you're representing each agent as doing their own personal benefit cost analysis. So really, to a large extent, this societal benefit cost analysis should flow fairly naturally from your modeling framework, which represents, you know, benefit cost analysis from a private level of each decision maker. So really the second part of my question is whether you'd endorse what I was just saying. I know it's a somewhat diffuse kind of question, but maybe you can comment on these issues.
Yeah, so I think that's a very good question. So about summary measures and using dollar amount as the ultimate metric that you use to transform societal, economic, and environmental variables. I think it's biased to some extent, because it would mean that ultimately the dollar amount is what we give most value at the end. So when I make these models, multi-perspective models, I'm generally tempted to leave the variables raw. So having environmental outputs and economic outputs and such. And then every decision maker is basically a multi-attribute decision maker and can assign a weight and can have their own, let's say, Pareto frontier that basically determines how these variables are combined together. So I would say that's more of an ad hoc approach to combined variables. So I don't know if I've covered the question adequately, but that's my intuition about it.
Other questions? Yeah.
So yeah, I had a question for Mamadou as well. So in your framework, you address the technologies and how they kind of, you call it generative entrenchment.
Mm-hmm.
I really like this concept, and I was wondering, how does it apply to institutions? And then with institutions, I don't mean organizations.
Mm-hmm.
We have the same background,
Right.
so we speak
Mm-hmm.
the same language. I mean like norms in behavior
Mm-hmm.
or
Right.
legislation that we put in place. I didn't really see it in the framework, and
Right.
so I was wondering, where is it? Then the second part to the question is, who can change it?
Yeah.
And can society do this as well, or only the polity
Right.
agents that you identify?
Right. So that's a great question. So the framework that's so in my announcement, that's part of what the framework should include. But I don't have the adequate treatment on how to model actually, and I think that's much more difficult to model than how technology changes. How do norms change and regulations and values and so on. So how do institutions change and that's actually how does culture change. And William Wimsatt, the person who has invented the term generative entrenchment, he has a couple of papers that deal with cultural change according to an evolutionary and developmental background. So he covers that a little bit. But in this model, I assume that norms and institutions are stable because I've not figured out the best way of modeling their change, which is a weakness.
This question.
The client has a adaptive order and disorder at the same time. How do you think you can take those lessons from there, translate it into more generalized society? And do you know if there's any research that's going on at this moment that would be studying that? Because I think it would be fascinating to
Specific studies I can't tell you, but I can say there's been a lot of experimentations like the mentioned, and there's some of these people are colleagues, so I know that they've tried out different things, but as a whole, I'm not totally sure if there's actual study out there. There could be. But as far as lessons learned, it is a very chaotic environment, and part of the reason that I mentioned the post-disaster and conflict zones, which are also zones I'm familiar with, such as Afghanistan and post-Sandy, that's where infrastructure breaks or doesn't exist to begin with. And one of the things that I personally see is in the post-disaster environments, when infrastructure breaks, unfortunately, the tendency is to try to reset up those same infrastructures in the same way. It's like Band-Aids, that you get a system that's supposed to be doing something, the system breaks, and the same system that should be able to adapt to it just puts it back the same way, and it's just going to break again in the same way. So that would be one lesson is, when things break or when it's sort of a chaotic environment is it's a scalability issue, really, right? It's a how do you find the ways to get institutions, if you speak of institutions, how do you get them to change these systems of operations that they're used to, their processes and policies? It's more of it's a social problem. So I can say that there are a lot of lessons that are being learned on the individual level or as even groups of people that is being taken out or back from Burning. I mean, Burning Man's been going on for a very long time, and it's just been getting more and more complex every year. When I first went in 2000, there was a max of 16,000 people. Now there's an upwards of 70,000. But the people that go there and they learn these lessons, they actually take it back into the everyday life, and then it gets propagated through their social environments. And now there are regionals worldwide where they try to replicate this sort of experimental social space. So there are a lot of lessons. This is a very complex question, and I'll try to not get into too much, but if you want to speak more, I'm happy to.
Any other questions? Yes. Sure.
Yeah, I mean, we generally perceive infrastructures as being permanent, cross-generational, and so on. And they move at a slower pace than what is structural. So, for example, with the Burning Man experience, it's very limited in time, but yet it occurs every year. What's the learning process? How is it bridged? Is it the same people coming back? Are there institutional roles that people hold when they come back? What's the rate of return? Is that
right? So there's, like I mentioned, there's the participants who come as theme camps, and there's some that have been coming for years. And I used to help run one of those camps, and then a village, which was a collection of camps. And there are things that are learned over time. You're like, oh, this totally works. That thing totally doesn't work. That shade structure, let's not bring that again. That broke, and then you learn over time. And then those ideas, they've actually, perhaps you've heard of the hexayurts that Vinay Gupta developed. That was because of Burning Man, and it was brought to Burning Man, and now there are tons of hexayurts at Burning Man, and it's a place and way to test them out. And there are people that come back, and these little lessons kind of propagate, right? And they become cumulative. What was the other side of the question?
So the knowledge management of it seems to me very. There's no knowledge management framework. How does it perpetuate itself? Where is the knowledge kept between one?
So a lot of it is through the communities themselves, but actually if you go online, there are tons and tons of projects that have been developed specifically for and because of Burning Man. And a lot of this is very much in the more informal, less institutionalized role, right? So this is where you'll find, I forget the name of the website, but like in the Instructables, for how to build different kinds of shelters. There are people who have even started businesses based specifically on this kind of experience, and then some who have translated these into humanitarian response. So there is a level of permanence that has been proven to work over time, and that has become more formalized and even institutionalized. I'm a volunteer for that, or actually I'm staff now, but I rose into that through my volunteering experience. And if I leave it, somebody else can rise into that. But a lot of it has to do with those cross channels, talking to other departments, talking to people who've been going for a long time, people who have had experiences in other places, like in Antarctica,
Thank you. All right. Thank you. And thank you to both our panelists. I think our panel finished a little early, so thank you.
It's good at flight.